In this work, we use a small team of micro-aerial vehicles equipped with magnetic anomaly detection sensors to detect and localize an unknown number of magnetic targets in an environment. We use ascending technology hummingbird quadrotors, which have an onboard magnetometer to detect cylindrical magnets, like the ones shown in the photo. For these experiments, we use a Vicon motion capture system to provide the robots with their pose at 100 Hz. We test our system using a single robot in hardware and a team of 1 to 4 robots in simulation. The robots use the onboard magnetometer to detect disturbances in the ambient magnetic field. These measurements provide only a single bit of information, indicating that one or more magnetic targets are within the field of view of the sensor. The green squares indicate the position of the robots, and the blue circles indicate the physical extent of the robot, plus a safety margin. The green circle indicates the field of view of the robot, which is only slightly larger than the robot itself. The robots use their noisy binary measurements to estimate the number of and the positions of the magnetic targets. Additionally, the robots must deal with both false positive and false negative detections. They do this using an estimation algorithm based on random finite sets. A candidate set is a set of occupied cells, with different estimates potentially having a different number of targets. The goal of the exploration task is to determine the set that correctly describes both the number of targets and the locations of the targets. The robots use an adaptive discretization of the environment. The shading in each cell indicates the probability that a target lies within that cell, with white being empty and black being occupied. The robots subdivide cells that are likely to contain a target and merge adjacent cells that are likely to be empty, keeping the total number of cells at a minimum. This allows the team to localize targets with high precision while keeping the computations tractable for real-time exploration. The robots follow the gradient of mutual information between the current estimate of the set of targets and the joint measurements of the team. By doing this, the robots move in the direction of the highest expected information gain, locally maximizing the rate of information collection. This strategy is known as information surfing. The team terminates the exploration task when the uncertainty about the target set is sufficiently small. Using our estimation and control framework, teams of various sizes are able to reliably and repeatably determine the correct number of targets and to localize all of the targets to within 10 centimeters, which is on the same length scale as the targets themselves.